All right, so we're about 50 people now. We'll get this started and let the oh, there we go, 50 on the nose. So thank you everybody. Welcome to Cleveland Big Data, virtual style. Normally, as folks know, this is normally the big event of the year for us. Unfortunately, because of COVID, we can't have the Mega Meetup that we would normally have in September. So we still have mega content. We're just going to have to do this in virtual style. But keeping with the theme of what we've been doing for the last 6 years is we've had a science leadoff in the first spot, and we're grateful to have Glenn Starkman from CASE, who's going to do a talk on astrophysics. And then we've got Dr. Piyush Mather from the Cleveland Clinic doing a COVID-related talk on healthcare with AI with Databricks. And then Tim Houlihan's doing a talk on our analytics performance. And then we've got Fanny Ye also from CASE doing another COVID talk. So I figured it was never bad to have more COVID talks during this time. So the more we can all learn about this, the better. So again, same rules. Yes, this is the famous, whoops, wait a minute, there we go. This is the famous timer, so we'll be using the famous kitchen timer, 20 minutes. It's a speaker's preference on addressing questions. So if you've got questions and the speaker is addressing them, just type them into the chat. And again, if the speaker can address them, then they will. If not, then they won't. So a few announcements. Again, this is the 10th anniversary of the Cleveland Big Data. Again, it was originally known as Cleveland Hadoop way back in the day. That's why the URL looks like that. But we switched, I think, back in 2014. So that is the first picture of the very first meetup. So I'd like to thank everybody that was there and has supported us over the years. We've had 62 prior events in the past 10 years, so this is the 63rd. And again, as most folks know, we're on a cadence now of 6 meetups a year. So you know, enough content to be interesting, but not too much that it overwhelms people. And again, as thanks as always, Chris Barrett, my partner in crime on this. I could not do this myself, so thank you, Chris. Also, the Linux Foundation for pitching in with their Zoom account. So I think I'm showing up on this meetup right now as Linux Foundation ODPI. I don't work for the Linux Foundation. That's John Murdoch's account. But again, thank you for the Linux Foundation for donating the Zoom account. And again, always thank you for the Big Data members. You guys make this possible, and the presenters make it possible with the content. Another tradition is the recruiting shout outs. So again, we can't do it in person with the yells, but what we can do is at least if you could type that into the chat, and I can read them out. So if there's anyone has any recruiting shout outs, please type it into the chat now. And or any other announcements. Here we go. McKesson's hiring a senior data scientist. Helen, why don't you put your email in there so people know who to contact. There we go. So helen.smith@mckesson.com. If you're interested in that. Anybody else? Pandata is also hiring. David, why don't you put in your email so folks can get in contact if you're interested in Pandata. Whoops, David@pandata.co. Tim Houlihan, Centric Consulting, is also hiring. Tim.Houlihan@centricconsulting.com. Chris, Progressive's hiring for a MongoDBA data analyst and machine learning engineer. Check out progressive.com for jobs. And again, I think I said so. Tim Houlihan at centricconsulting.com for the Centric Consulting one for a senior data architect. Well, joke from Piyush. I wish I was called a data scientist. You're a doctor. You already have a cool title. You can't have all the cool titles. So we can only see the panelist comments. Not sure. So it looks like we're at the end of the recruiting shout out. So again, chat broadcast all. So everybody should be able to. Yeah, everybody should be able to see. Is there any? Can everybody see these? Oh, it's all panelists. Oh,
yeah, that's it.
Okay, my bad. Okay, so it should be all panelists and attendees, I think. Yeah. Okay. Well, we're gonna have to. There we go. Is that better? Well, we'll go on to the we'll go on to the first presenter, which is Glenn Starkman. So Glenn, take it away.
Great, thanks, Doug. It's great to be here, and I wish I was seeing you all in person because then I'd be running around the stage, jumping from side to side and stuff. But I want to tell you about a really big data problem, which is the searching for the topology of the universe. The data problems don't get any bigger than that. So let me start by saying, let's see, that light travels really fast. As you all know, I'm sure, about this far in a nanosecond, which means that if you're looking at the solar system, light takes hours to cross from one side to the other. And if you're looking at, say, the night sky and see stars up in the sky, which is often hard in Cleveland, but if you go out to somewhere dark, then those stars, the light is traveled light years, which means it's taken several years or tens of years or sometimes even hundreds of years to travel from some of those stars to us. But our galaxy, the Milky Way galaxy, which looks a lot like this one, NGC 7331, is a spiral galaxy, about 100,000 or so light years across. So when we look at the far reaches of the galaxy, we're seeing light that was emitted before our ancestors left Africa, probably. And when we look at the most distant things, this is the Hubble Ultra Deep Field from 2018. This is a picture taken by the Hubble Space Telescope, pointing to the the darkest part of the sky, where there doesn't appear to be pretty much anything there, and just sitting there and integrating for a very long time. And you discover there's lots of stuff there, lots of galaxies. The most distant of those galaxies, the light came from them, left them over 10 billion years ago. In fact, over 12 billion years ago, nearly the age of the universe, which is about 13.8 billion years. So that means that that space is big. And for all you fans of The Hitchhiker's Guide to the Galaxy, you know that. But I think we all know that space is really big. Now, what you may not know is that space is pretty close to flat. And so the question is, well, what does that mean? I think you would believe that if I showed you a map of Ohio, you know, I could make a nice flat map of Ohio. So Ohio is nearly flat. What that means is that if I draw two lines across it, and I'm going to do that on a piece of paper. So here's a nice flat piece of paper. I think you can see that. I'm going to draw two lines across that piece of paper with my ruler. And just like these lines across the image of Ohio, they start out a certain distance apart and they stay the same distance apart. We call those parallel lines. And so on a flat piece of paper, parallel lines stay the same distance apart. So that makes Ohio flat. Also, if I draw a triangle, I can use my ruler to draw a triangle on a piece of paper, right? And I drew this triangle on the state of Ohio. And if I draw a triangle and then I go and measure the angles at the corners, and there's of course 3 of them, then the sum of those is 180 degrees. And that's another thing that makes Ohio flat, okay? Well, you might ask, well, what else could it be? But of course, if you look at the surface of the Earth, I think all of us know that it's not flat. And I could take two parallel lines. Here's one line starting at the equator and heading due north. Here's another line starting at the equator and heading due north. And first of all, you'll notice that those lines that were both heading due north meet at the North Pole. Also, if I join them by another straight line along the equator, then those angles at the equator were 90 degrees because the line on the equator went east to west and those other lines went straight north. And so the sum of those angles is B is 90, C is 90, and A is whatever it is, depending on how far apart I started. And so the sum of those angles is bigger than 180 degrees. And so not all surfaces are flat. So Ohio is nearly flat. Actually, of course, Ohio is pretty big compared to the size of the Earth. I mean, is modest compared to the size of the Earth. Cleveland's pretty flat. What about space? In other words, if I put a couple of parallel lines out in space, two lines that started out, so that if I put a line across them, the sum of the interior angles would be 180 degrees. Would they stay the same distance apart, or would they get closer together, okay, like they do on the surface of the Earth? If I drew a triangle way out there in space, and I added up the sum of the angles of the triangle, would they add up to 180 degrees, or maybe they'd add up to more, like they do on the surface of the Earth? So, so here's a map of the surface of the Earth, and we need a different sort of map in order to ask this question about space. We need a map of the universe. Okay? And here's a map of the universe. It's a pretty boring map. It's a map originally made by this antenna, owned by by Bell Labs back in the mid-1960s, and they pointed it up at the sky, and they discovered that the sky was glowing at the same temperature in every direction. That's why this map looks so boring. So what I've done here is I've taken the surface of the sky and peeled it out to make a map just like this one of the Earth. You know, you can imagine this wrapped around the Earth and peeling it out. So this is a map of the round Earth stretched out onto a flat piece of paper. This is a map of the round sky stretched out onto a flat piece of paper or onto my screen and yours. And it is really, really boring, which is worth a talk all on its own. So making that map earned Penzias and Wilson a Nobel Prize. Since then, we've made much better maps. First with this satellite called COBE, the Cosmic Background Explorer. More recently with this satellite in the early 2000s, called wmap. And most recently with this satellite of the European Space Agency called the Planck satellite. And these days with a couple of telescopes, one at the South Pole, one in the Atacama Desert of Chile. Okay. And they make a map of the sky, right? They point all over the sky, measuring the temperature of the light coming from everywhere on the sky. And this light is light that was emitted when the universe was about 3,000 degrees, comparable to the surface of the sun. And that light has been traveling through the universe for 13.8 billion years. And it's coming to us from every direction. And as I said, it's pretty much the same temperature glow in every direction. But if you look really carefully, like we can do with satellites like WMAP or Planck, we can see small differences. And I have here, you can see a globe version of this, you know, on the surface of the sphere. But the one I'm showing you on the screen has been unwrapped in that nice way, so that the top is up here, the bottom is down here, and then I've peeled this open and laid it flat for you to see. And here's a more detailed one made by the Planck satellite in the early 2010s. Now those bright and dim spots, so those hot and cold spots, are actually imprints of sound waves that those sound waves were traveling through the universe when it was less than 400,000 years old, because that light was emitted when the universe was 400,000 years old and has been traveling through the universe for the last 13.8 billion years. So you can imagine sounds traveling through the universe. So here's a picture of a sound being made at the center. The sound travels out. Then as the universe expands, the sound kind of stops traveling, it gets frozen in the plasma, and then we get to see the impressions of those sound waves. Now, we got to see them from when those sound waves travel at the speed of sound, which traveled pretty fast back in the universe, but not the speed of light, but about a third the speed of light. And so those leave patterns on the surface of the sky. Okay? And the size of those patterns is what we see here in this picture. We see all these patterns. You notice a kind of characteristic size shown by these green arrows. And so if we're looking out at those with a telescope, they make a nice triangle that we can measure. Okay? And we can look at that and look at the sum of the angles of that triangle and figure out if they add up to 180 degrees, like they would if the universe is flat. Okay? So if the universe was curved like the surface of the Earth, like we call it positively curved, that's that thing on the right, then those patterns would be a little bit bigger. If it was what we call negatively curved or hyperbolic, they would be a little bit smaller, and if it's flat, they'd be a particular size. And we go out and look, and it's really, really close to flat. So unlike the surface of the Earth, the universe appears to be flat. So the Earth is round, but the universe is flat, or at least very close. Okay? It turns out, though, that there are many ways to be flat. Okay? So what do I mean by that? Well, here's a flat piece of paper. But if I take this flat piece of paper and roll it up into this nice cylinder, you'll notice that if I went to the corners of my triangle, 1, 2, 3, and measured the angles, they would be the same. And if I added them up, they'd still add up to 180 degrees. So this cylinder is flat. It doesn't look flat because I've had to roll it up in 3 dimensions and it's a 2-dimensional surface. But if I could be an ant crawling around on the surface of this cylinder, it would be as flat as a normal piece of paper. So the first surface of a cylinder is flat. Actually, so is the surface of a cone, because I can do the same thing and I still have my triangle on the surface of this cone. And so cones are flat. And this is even harder. But you notice to make my cylinder, I rolled it up that way. I could have rolled it up this way. Okay. And a torus is just doing both. So in fact, the surface of a torus is flat. So there's many different ways to be flat. And the question is, which way is the universe flat or nearly flat? And how can we tell? And so one way we can tell is for me to start by telling you that there's a different way to picture this idea of the universe having what we call non-trivial topology or being multi-connected. It's like living in one of those 1970s video games where, before the time when there was enough computing power so that if you left the edge, you generated some new universe. Imagine instead, you went off the side to the right and you came back from the left. You went to the left, you came back from the right, front to back. So it's like living in a cube where if you leave one face of a cube, you come back from the other side. So imagine I'm sitting here making my experiment, looking at this light from the early universe called the cosmic microwave background, and I look at and see it. It's all coming from a sphere centered on me because it's been traveling through the universe for 13.8 billion years. And I measure this nice pattern. Here it is. This is what I measure using my microwave antennas. But then if I run far enough over to the, through the side of my video game and come around to where I was, I make the same experiment over here, okay? And I do the same experiment and measure my microwave background, but this version of me is doing it over here, and this version of me is doing it over here. And if those 2 copies of me are close enough, in other words, if the shortest path around the universe is short enough, less than the diameter of our universe, of our observable universe, then those 2 will intersect. Okay? And you can see that here. I think you can see my pointer. Those 2 balls, the places where the light from the early universe is coming to us from, that us looking out, we see it in one direction. if I'm standing over here, I look out, I see it in this direction. If I'm standing at the center of the left sphere, I see it to the right of me. And those are two places on the sky, one to my right, one to my left, where I see the same places from different sides. So if I'm seeing patterns of hot and cold around that sphere, one of them will appear here and the other one may appear here, and I can look out and look for such pairs of circles that have the exact same pattern as we go around them. Okay? So I would find pairs of circles on the sky that have the same pattern of hot and cold temperatures. And so we want to go look for such pairs of circles. Now, the thing is, this is a really tough search because when we go out and measure the microwave background these days, we have about 10 million individual pixels on the sky. And so what I want to do is I want to look for circles. It turns out these circles can be centered on any pairs of places. These pairs of circles can be centered on any pairs of pixels. Okay? They can have any radius. They have to have the same radius. And they can be turned in any way compared to each other. And then to compare them, I have to multiply all the I have to compare all the temperatures around those circles, and that's an n to the 7/2 problem. And n is 10 to the 7th, and 10 to the 7th to the 7/2 is like almost 10 to the 25. It's 10 to the 24.5, which is a very big number, very hard to do. And so we have to improvise a little bit. So what we do first of all is we realize that most of the interesting information comes. We don't need all those really, really tiny pixels. We can make do with about 100,000 pixels, about a degree on size. In fact, for our first look, we can make do with about 10,000 pixels. We can use some tricks of using some FFTs to make the comparisons and reduce to 10 to the 3rd, and so we can look for circles. And we've shown that we can do this. Here's what happens if we do this on a simulation of a universe that has an interesting topology, in which you can go around and you see these bumps. These are bumps in some statistic. And if it was a boring universe in which you couldn't loop around it, you'd never go above this red line. You see, we go above the red line lots of times. And that was, in fact, that simulation was made by someone who didn't tell us what was there. And we found all of the circles down to about 24 degrees. But when we did this on the real sky, we found nothing. So that told us that the universe had no circles. That's not quite the same as saying that it has no interesting topology. We'd like to keep looking for things that wouldn't have produced those circles. And the way to understand that, how we look, is to understand that the shape of a drum determines its sound. So I have here two drums, okay, that are about the same size. And this drum sounds different than this drum, not just because they're different tautnesses, but also because they're different shapes. So different shaped drums make different sounds, and different shaped universes will have different sounds traveling through them. And so remember, these hot and cold spots were imprints of sound waves in the early universe. And so big drums will have low notes that smaller drums are missed, but also different shaped drums will have different timbres. In other words, when you make certain sounds on one drum, you'll make other sounds at the same time. Try to play one pure note, you won't succeed. You'll play all sorts of notes that go together. And so our theory of the early universe tells us that in an infinite flat universe, you get a cacophony of notes, all of equal volume, kind of noise. But we'd like to look for correlations between those different notes. Now, the problem is there's about 10 to the 7 notes and about 10 to the 14 different pairs of notes, and we have to compare each of those pairs of notes between what we see on the sky and what we'd expect from each different possible shape of the universe. And there's lots of different shapes of the universe. In fact, it's a 12-dimensional parameter space, and that includes the shape of the universe and also our position and our orientation within that universe. So it's a really, really big data problem, okay? So what we measure when we go out and do this is a cacophony of equal volume high notes. Those are small pattern. And this strange, harmonious, somewhat quiet low notes that seem to be correlated with each other. They are too low, and they're also too organized, which seems to be a hint, perhaps, that what's causing this organization is the shape of the universe modulating the noise of the Big Bang. Okay? And but to figure out what shape and whether this is in fact the explanation is a really hard data and computational problem worth solving, and that's what we're trying to do. and I'm happy to take some questions.
That was awesome. Thank you, Glenn. Let's see, folks in the chat, if you've got
And I'm
questions.
trying to find the chat. Give me a second. I don't see the chat, so.
I don't see any questions coming in on the chat. We'll give it a little bit. Someone says, sounds like music to our ears. That's funny.
Can this be applied to commercial purposes? Wow. I don't know. I'm happy to think about that once we figure out how to do it. We haven't figured out how to make this comparison yet, not to the full extent that we need to. So this is what we're busy trying to think about, is how do we make this comparison? How do we can we do it in a deductive way where we see the odd patterns, where we know the odd patterns we see and find a shape that might fit them? Or can we do an exhaustive fit of all the possible shapes and all the possible patterns? That's a really, really big data problem. And or is there some AI approach that would help us? We're all trying to think about this.
That's a time right now. We have to move on. Glenn, thank you very much. Real and virtual clap here, but thank you very much for doing that. That was fascinating. Next up is Dr. Piyush Mather. There we go. And whenever you're ready.
All right, can you see my screen now? Just want to confirm that.
Yes.
All right, perfect. After that world, or I should say like a universe tour back to Mother Earth, where the West is getting smoked out, there's a hurricane down south, and of course we are all still in the middle of the COVID-19 pandemic. So going to talk about, what have been some of the challenges with AI applications in healthcare during this COVID-19 pandemic. Myself being a physician, working with a lot of different data scientists, machine learning engineers, and with some training and background in machine learning and AI myself. So this was an article that came out earlier in the year, somewhere around like April, and it talked about, how AI has been a failure during this COVID-19 pandemic, and how there has been a total hype about AI, and the COVID-19 pandemic is essentially unraveling this. And this truly broke my heart. It kind of reminded me of this movie, Superman Returns, where Lois Lane had written that article that the world doesn't need a Superman, and ultimately she realized that that was not true, and there was definitely a need for a superhuman to help the Earth and the human beings. If you think about where all this started, again, this article, which was published in AI in Society, also talks about early in April that AI has its limitations, especially has met its match in COVID-19, and it's a true problem for AI. And if you truly think about it, it wasn't an AI problem, it was more of a human problem. It still is more of a human problem than AI problem. We talk about the discovery of COVID-19, there were some signals that were initially captured about COVID-19. There were these signals that there's some unusual pneumonia that is occurring in China. And that was firstly detected by this Boston Children's Hospital network called HealthMap. And that's what made people realize that there's something unusual going on over China, and that there is an possible outbreak of things. Subsequently, people also realized that not just from the medical point of view, but even when you looked at social media texts, there were these texts and this chatter about some unusual disease. People were searching and were talking about this unusual disease called coronavirus and pneumonia. And that preceded these outbreaks in these different areas by a significant time period. So there were all these signals that were there that were being picked up throughout the world. But just that we weren't necessarily realizing, or we weren't realizing the magnitude of how big this pandemic is evolving to be. And if you are interested in looking at and working more on that particular data set, here is the data set that is available on Kaggle with the tweets, and you can work on that more to look at social media tweets regarding COVID-19. As this pandemic evolved, there was an enormous need to understand COVID-19 and related things in a better way. And that's where some of the tools started evolving very quickly. There were a lot of citations, there was a lot of literature search that was needed. And that's where a lot of tools started getting built because we really needed to gain the knowledge. And that's where a lot of machine learning tools were showcased. Here is a COVID NLP, which was able to look at various different publications that were put out by WHO and was able to distill it using various natural language processing tools so that people could understand and quickly search and find what they were looking for. So there was a need to distill all this knowledge and information and weed out what was misinformation and provide helpful information to the scientists and physicians working across the world. And similarly, novel tools came about. So there were a lot of chest x-rays being taken, and people were realizing that other than just the tests that are being done, like the PCR tests that are being done, there were some significant findings on these chest x-rays that could be utilized for diagnosis or detection of COVID-19. But if you remember, these tests till a few months ago were not easily available everywhere, but these chest x-rays were. So there were a lot of these tools that were starting to be built and put out there that would help in detection of COVID-19, some of them with a pretty significant specificity. At the same time, there was a need to quickly start working on vaccine and drugs so that we could either prevent this disease or treat this disease. So simultaneously, early on, as the genetic makeup of coronavirus, SARS-CoV-2 was discovered and shared, there was an accelerated work occurring in the drug discovery area using various machine learning or AI tools so that we could get closer to prevention and therapeutics for the same. If you're interested, this one just came today. This is the Kaggle Vaccine competition. What has happened is, as you know, Moderna has a vaccine, but that vaccine requires stability in certain temperatures for mass production, for transport and distribution. What they're realizing is that they don't know the degradation time period at various different temperatures and time points. So this open vaccine competition just got launched today, where they are looking to see how mass production can be done and these degradation times can be measured. So would encourage everybody to think about participating in this, and the data set is available through the same. And going beyond that is the important aspect of patient monitoring, because all of a sudden we had to expand this monitoring aspects into the within the hospitals. We had to think about constructing hospitals which were constructed in certain areas which were not hospital spaces. And we had to even think about remotely monitoring patients so that we could treat them without bringing them into hospitals. And a lot of tools since were built so that the clinicians would be able to provide healthcare from a distance and in a safe manner, and have been applied now. With BrainX and BrainX community, we have been working on the same. We started researching COVID-19 mortality in the United States, and we were curious about the interaction of various socioeconomic, geopolitical, weather patterns or travel with the COVID-19 mortality. So we started off by creating our own data set, which we have made available. It's available and accessible for free on Figshare. And we encourage others to use that data set too, in the spirit of open access and sharing with everyone. And from that, we were able to have a collaboration constructed across continents between US and India, where one of our colleagues, Dr. Pritesh Sethi, who's assistant professor at IIIT Delhi, and our team, using that data set, constructed two different models. So the first model that we created was a cat boost regression model that is on the left of the slide, and through which we developed this explainable SHAT feature importance distribution. And the second one that he independently developed, independent of our efforts, developed was a random forest traditional model, and he used the Baruta feature importance scale. And it was interesting that although we used the same data set, developed two models completely independently, but both of them showed similar results and similar patterns, where the population density, pre-existing medical conditions, certain racial factors like African Americans, certain travel data like direct flights from Wuhan or Europe did have a significant impact on COVID-19 mortality. And these are machine learning models. So these are not looking at any pre-existing research. These are independent machine learning models that are looking at the data that we had provided to them based on US population statistics. So that was really interesting for us. Beyond doing our own research, we have also been at BrainX community sharing the research being done by others. And this was one of the recent BrainX community live events. We do these every month. And you can go to BrainX Community's YouTube channel to see the ones that you might have missed in the past. And this was our August event where Dr. Lara Jehi, who's the Chief Research Information Officer from Cleveland Clinic, presented this model for individualized prediction of COVID positive tests that was developed at Cleveland Clinic using patient data. So beyond doing our own research, we have been sharing research by other team members or other groups too. At the end, what we have to realize is something that I published earlier in the year, that AI is not a magic pill. You know, we have a lot of expectations, but till the time we don't have reasonable data, till the time we don't have the ability to construct good models, till the time we don't have the ability to validate some of these models and ask good questions, we are not going to be able to use AI in a meaningful way. Again, some of the solutions in the same article that I shared was that we have to, of course, use a patient and provider-centric approach. And the oath that the physicians take is to do no harm. Again, try to stay away from all the politics that might be there, and showcasing the leadership.
Hey, Piyush, we lost you. We've got all gray here.
Yeah, I'm sorry. I'm not sure what happened. Just give me one moment. You know what? I was pretty much on the last slide. So I think I'm going to end my presentation there.
Okay.
And I'll be happy to take any questions.
Okay, so we're taking questions now, and please type them into the chat if you have any questions. So I didn't know about the Kaggle Vaccine competition. That was just today. Is that right?
Yes, that just came out today. I just received the notification today for that. Yeah.
And were there any, so the analysis also of the chest x-rays, has anyone had any initial observations around COVID prediction from that?
So I think a lot of that is in work. And there are some models that are showing specific, very high specificity, but there are CT scan models that have also come about in the meantime, which probably are more granular and give you better depth. But all these require validation. All these require external validation. And that is still lacking significantly. So till the time we don't have good external validation of these models, I don't think we can say, confirm the findings, or we can say the superiority of one versus another.
Got it. We've got a question here from Randy Detmer. Did your team use R or Python for your analysis?
So that's a great question. We always use, or I should say, I always use Python, and my friend down in India used R for that.
Got it. Thank you. So I think we're, wait, we got another one? No. I think we've, so is one preferred over the other?
So if you look at the background of Python versus R, R is more of a statistician's language, whereas Python is more of a data scientist or developer's language. So most of the times, people will end up using Python if they are going to use it for further development, whereas most of statisticians will use R. In my personal opinion, I find Python very easy. A lot of tools are being built around Python. And the second advantage of that is that there is a much bigger support group for Python users as compared to R, as you can imagine.
Super. So now the questions are starting to roll in here. So do Mike's question. I'll read them to you, and you can answer them in the order in which you want to. Are the weekly Cleveland Clinic COVID talks open to the public? And then a question: what are the greatest obstacles for you in doing this kind of analytic work?
Yeah, I think great question. So I'm not sure which weekly Cleveland Clinic talks you're referring to. There are BrainX community monthly sessions that we do, and I can share the link over here. And those are open to everyone. Those are open to public. The links to those are posted on BrainX community webpage. And then if you miss it, the YouTube videos are available again through brainxcommunity.com or through the BrainX community YouTube channel, if that's what you're referring to. I'm not aware of any specific Cleveland Clinic COVID talks. And the second question was, remind me again, regarding?
It was regarding the greatest obstacles for you in doing that kind of analytic work.
Yeah, I think the biggest obstacle is access to data. And I think the access to data has been evolving. So if you go back to March or April, there was hardly any data available. Johns Hopkins was the first one to put out some COVID data, but then over time period, these data sets have evolved and been made available. And that's why we also made sure that we make our data set available to everyone so that they can either try to replicate or build on what we did and maybe have even better results than what we had. So data has been the biggest challenge for all of us. Good quality data has been the biggest challenge.
Okay, we got other questions. The Institute for the Science of Origins has a series of public talks and regularly includes COVID talks. You can go to origins.case.edu for looking for other events. Okay, you got another one. Does it seem that AI usage is being newly transitioned to dealing with COVID and the pandemic? Or is this building off of previous public health applications of AI usage? Is the paradigm shifting for AI usage for public health?
I hope so. I hope that the paradigm is shifting, and I hope the paradigm shifts more so on the data side. Because if you think about healthcare data, I think Doug knows this very well. All the data has been in silos. You know, we haven't had true big data. We have had little silos of data everywhere, and data sharing has been limited because of various different concerns, ranging all the way from HIPAA or privacy, or sometimes just pure ego, and how the funding is associated. So I hope the biggest paradigm shift that takes place is in the space of data, where people realize the value of data sharing and accelerating research that we have seen with the COVID pandemic. And I'm very hopeful that that'll shift. In terms of the models, of course, we will learn from this. We'll learn a lot more from this. Even if you think about applying natural language processing tools, which are mostly built on either social media text or the web-based text, the time that these evolve to understand healthcare text better, I'm sure a lot of these tools will be much, much better for us in the future. So yes, I think that there is a significant impact of this COVID-19 pandemic, and I hope it will be in a positive way in the future for us.
Interesting. We've got 2 minutes here. If there's any last questions, hopefully I didn't miss any. Yeah, I think the other comment about the weekly talks was related to your comment about Dr. Laura Jehi in her talk. If so, as long as, I think you had mentioned that she had done a talk in a series. So if it's the same thing, then I think that's addressed.
Yeah, I just posted the YouTube channel link for her talk.
Okay.
And the BrainX community webpage link is also posted, so you can go there. And all the talks and their links are available over there. And everything over there is free and open access. We provide everything as open access.
So we've got one more question from your perspective. Is your research effort hampered by a lack of uniform standards for collecting COVID data?
Yeah, that is true. I think that's a great question. So the lack of standardization is a prevalent problem. I'll give you a very simple example that you would relate to. When we were looking at the data from all different states, you would expect that the data on how many patients are on the ventilator would be a standard report. That's not true. Some states reported how, on a regular basis, how many patients are there on the ventilator, whereas a lot of states did not report that. So when you want to construct a model or when you want to do further research on that, if you have missing data, which is pretty significant, then you're limited by that. So standardization and the quality of the data sometimes was a big problem too, in terms of what's truly COVID-19 and how it is being diagnosed. If you think about COVID-19 diagnosis with RT-PCR versus certain other rapid tests, there is a higher false positive rate with certain tests. So that does pose a limitation, and standardization of that has been a challenge, but less of a challenge than availability of data itself.
That's great stuff. I'd like to thank everybody. Piyush, thank you so much for doing the talk. Everybody give him a round of applause, virtual claps. Thank you very much. That was fantastic. Next up is Databricks.
All right. Thank you,
Jessica
Doug.
and Miguel, take it away.
Awesome. Yep. Let me share my screen. One second. Zoom was asking for permission. Sorry about that. There we go. And share. My screen should be visible now.
It sure is.
Awesome.
If you just want to put it in present mode, then I can jump in.
I'm seeing it in like edit mode instead of present mode.
Yep. Perfect.
Wonderful. Well, thanks for having us, Doug. I will do some quick introductions. I am Jessica Shifley, one of the account executives with Databricks. And then we have a few other names on the screen. Scott Kelly, another account executive out of Pittsburgh. Ryan Gordon, an enterprise solutions architect, and then Miguel, who's going to be presenting today, another one of our enterprise solution architects. So we just make up a small team of the overall Databricks group across the country. But for those of you who don't know who Databricks is, I just want to give a quick background. We are a software company that's a managed service, essentially a unified data and analytics platform that allows for collaboration across 3 different personas: data engineering, data science, and business analysts. And today we're going to focus a little bit more within the data science realm, talking about well, actually 3 different things today: Spark, Delta Lake, and MLflow. We're the creators of all 3. So, and some of you guys may have heard of us in conjunction to Apache Spark. So today, if you want to go to the next slide, Miguel. Today, we're going to talk about a popular use case, specifically within the retail industry. So we have over 5,000 customers across the country, but specifically in retail, we're going to use that as an example today so we can kind of get into the data and have fun a little bit with showing you an example. But this is just a quick statistic. 17% of consumers, actually, let me just, 17% of consumers shifted away from their primary store in favor of buy online, more hygienic offerings. So a popular use case that we see from our customers have to do with content personalization, customer churn, recommendation engines that really allow them to drive higher revenue, marketing efficiency, customer retention, and just understanding their customer better. And ultimately today, what we're going to talk about is how you're able to do that, how you're able to get closer to your customer through data. And so that's where Miguel is going to come in and take over and just kind of explain how to utilize Databricks to make this happen. So if you want to take over, Miguel.
Absolutely. Yep. And just to make it more specific, I want to focus on one topic, which is customer lifetime value. And part of the reason was when I heard about the event happening and our opportunity to participate, I thought it could be useful to break away from the other topics, just kind of a change in pace. And also because I had the opportunity to work at Etsy in a data scientist capacity, and I was responsible in part for CLV models and CLV calculations. And I found that work to be pretty interesting from the data science angle. And I want to cover that today while also introducing what Databricks is and what the different components that the platform offers for data scientists. As Jessica mentioned, the roots of the product are all in open source. So Apache Spark, Koalas, Delta, Redash, MLflow, those are all parts of Databricks and they're all open source. Very specifically, and this is something that happened recently, I added this as the session was starting because I know that Linux Foundation was mentioned as a collaborator or a sponsor of the event. So MLflow is now also part of the Linux Foundation. So we're benefiting from that, having that governance structure and that wide community that comes with the foundation. And in terms of introducing what Databricks is, and I'll move through this rather quickly so that we can jump into a live demonstration. So that's why I had the screen, not a presenter mode. When I first started sharing, I was making sure that I had some the notebooks that I wanted to show you. But basically the idea here is that in order for us to do data science work, and we've been covering some of these scenarios in the last few sessions or in the last few speakers, the idea is that we're going to have raw data coming into an environment or into a tool, and we need some way to store that data in a format that's optimized for high performance, a way to process that data in parallel, usually when we're working with big data sets. And that's precisely the goal of these two technologies. One is to be a distributed processing engine. I'm sure a lot of you are familiar with Spark. The other one is to provide a data format that is suitable for distributed processing, and that brings some of the data reliability things that we expect from databases or data warehouses into the world of a data lake. But ultimately what we want to go through is a cycle that, if we oversimplify it, it's going to look something like this. It's going to be preparing the data. We're going to build, optimize, tune a model, and then eventually we're going to deploy that model. And the underlying theme here is that MLflow as a model lifecycle management tool should help us to go from data prep to deployed model with more ease. And the other thing that, if we think about usual challenges that we face as data scientists, is having flexibility in environments and infrastructure that we want to run. We may want to run a specific model with X number of nodes, that each node has specific libraries or specific runtimes, that sort of thing. So having the flexibility to try out different things without having to commit to anything too rigidly, or just maintaining that efficiency is part of what Databricks and MLflow specifically within that offers. So the cycle is going to look something like this. We're going to go from having, as part of the tools that we're going to be working with, a myriad of libraries, and MLflow along the process is going to play different roles. At the beginning of the process, it's going to serve as a way to encapsulate models into different flavors and maybe one flavor is Python based, another one may be Spark based or TensorFlow based. Then we're going to have tracking of experiments as we iterate on those models and we tune parameters, we change training data, all of these things. Then we're going to have a way to provide transparency into that experimentation process and into the life cycle of the model through development stages. So we can go from staging to QA to prod, and eventually even archiving some models. And then ultimately we want to be able to expose the model or actually use it to make valuable inferences. And that may be through a cloud inference service, it may be through a Spark function, it may be through containers. There are multiple paths, and MLflow is designed acknowledging that there will be different libraries that a user will be using. There's a life cycle, and there are multiple paths in which you would want to take a model out to production. So, and I'm mentioning all of this with the idea that it should help us understand the tools that we'll work with. And what I want to switch to now is to Databricks notebooks. So they're going to, for those of you who haven't used Databricks, that's not a problem at all. The Databricks notebooks are going to look and feel very similar to Jupyter notebooks. So you should be pretty at home for those of you who have used Jupyter. And there's no bias in here, but I am, most of the content that I'm going to show you is going to be Python based. So I know that there were some questions about R versus Python and all that. The notebooks do support R, Python, SQL, Scala. It just happens that the content that I'm going to be showing you is going to be Python based. And the last thing from a slides perspective that I wanted to show you is the idea of a machine learning runtime. And that has to do with the fact that, as Jessica alluded to, Databricks offers managed Spark environments, and those managed Spark clusters can have preloaded libraries into them. And we have a specific ML runtime that both comes with common data science or ML related frameworks or libraries, as you can see here, TensorFlow, XGBoost, Keras, scikit-learn, and a few others, but also the ability to extend that or to customize that using Conda. So the idea is that if we can allow you to prototype models and to test them and to iterate on different components, then we should make it faster, easier for you to develop and eventually get value from that model. So in terms of CLV, and I'll use this as a way to transition into the live environment, when we mention customer lifetime value, we usually mean something like this, where we say, we have multiple customers, they're going to be engaging with us. Let's say we're a retailer, or either online or brick and mortar, but they're going to be engaging with us multiple times, hopefully multiple times throughout their lifetime as a customer. Some of those interactions or engagements may be higher value, some may be lower value, and that's going to aggregate up to a full lifetime value. And it's going to look very differently from one customer to the other, or from one cohort to the other. And then we should be able to roll that up into different customer segments that have similar engagement patterns and similar individual lifetime values. And we should also be able to have metrics such as the average CLV for one customer, and just understand what that looks like. Are we expecting to make $1,000 of one customer throughout their entire lifetime? Or are we hoping to make hundreds of thousands of dollars in terms of lifetime value from a customer? And from, like I mentioned, from the time at Etsy, it's definitely, for those of you who are familiar with the platform, CLV wouldn't be in the hundreds of thousands of dollars per user or per customer. It may be probably in the hundreds or in the thousands. So I do want to show you a live environment so that you can understand how this would be helpful for you to actually play around with data, take a stab at calculating CLV if it's relevant to anyone in the audience, and also just know that you have a myriad of tools, like I said, to work with. One of the things that I'll highlight for those of you who are doing either academic work or just playing around, there is a Databricks community edition, so it's free to start using, no cost, no licensing, no cloud infrastructure costs associated to it. And this is an example environment. So it's going to have a few sections that are key to what I'm going to go through now, including the ability to spin up Spark clusters, and some of those clusters maybe with that ML runtime, as I mentioned, the ability to bring in data. One of the things that I'm going to go through two notebooks briefly, and they're aligned with two specific blog posts that we have. So this is part one of those blog posts, and I'm going to share the links before I drop off with the audience. And then there's part two of these, and you can see that the blog posts are going to take us through customer lifetime value, and they both have their corresponding notebooks, which are the two notebooks I'm going to go through in a little bit. So if you wanted to take a stab at this, all of the data sets needed to run these notebooks in your own environment are preloaded into our community edition environment. So you're going to have access to the data sets without having to do anything. So coming back to this, I mentioned the clusters that are going to be necessary, but jumping into the notebooks themselves, this is something that I mentioned that you should feel pretty at home when you look at it for the first time. There are certain things that are specific to Databricks and what I'm looking at. The first one being that I just attached this notebook to a cluster. In this one specifically, we're going to be calculating the probability of future customer engagement. So coming back to this, how probable is it that we're going to see a customer come an nth time after some prior engagements with the customer? And we're going to go through normal notebook setup things, including setting up libraries or additional libraries beyond the ones that come preloaded. We may do data manipulation or data prep as we interact with it, some exploratory analysis, some visualizations, and ultimately we're going to get closer and closer to wanting to train a model with this. So these are just examples of SQL, some Python that's used to train this. And in this case, we're going to eventually get the data in a state that's suitable to actually train a model with this. And one of the things that I kind of skimmed through when we're looking at this is the fact that even though we're used to having notebooks like this one that are that allow us to write Python or that allow us to write Scala, SQL R, there are certain things that are specific to this. So for example, if we wanted to make this Google Docs-like experience and start collaborating, drop in comments, tag people, co-develop live, that sort of thing. And that's an example of how you would interact with this notebook. The second notebook is going to be pretty similar. Let's see if I have MLflow in here as an example. Let's go and take a look at this. There we go. I think it's in this one. Let's go to cell number. Perfect. Let's do this. Awesome. And let's go. Perfect. So let me go into command, I believe it was 80, and I'll show that to you. And almost there. There we go. This is 78, 79, 80. Perfect. So this is what I wanted to show you. So in this specific line, we're using the MLflow API, which is preloaded into the ML runtime. And this is an important command for us because it's going to give life to what I mentioned earlier about the ability to track experiments and compare parameters. And if we wanted to look at this, what it would look like if we were actually running this notebook right now, this is an example of another one. So this is another notebook, not related to CLV anymore, but now showing the MLflow start run API or start run call. And in this case, we're training a specific scikit-learn model. And you're seeing that we're logging the model, we're logging parameters, we're logging metrics, artifacts. And this manifests itself in this right-hand sidebar or in this, this experiment run sidebar. And this is one thing that allows us to not only track our experiments, see how different metrics or different parameters are changing, but also to track our specific runs and take a look at them. So this is one way in which we can start making our model training process much more transparent. So now we're going to have specific parameters associated to this run, maybe the number of estimators, the depth, the metrics. If we wanted to see the actual model in pickled format, or if we wanted to just understand what libraries you use, what versions. So these are all steps that help with that process of making the model lifecycle or the model management lifecycle process much more simpler. And this, if we take a step back, all of this would roll up into something like this. So this is a model registry. So in that case, let's say we developed a CLV forecast model in some way in the first two notebooks, then we can register as a model in our model registry, and now we can track, hey, we have this specific Airbnb price forecast model or CLV model, and we're going to have multiple versions associated to it. One version may be in production, one version may be in staging. If we wanted to go into it, we can actually see different versions, compare the performance of them. So these are pretty standard operations that we would do day to day as data scientists. Maybe we want to compare the different metrics associated to these models. If we wanted to even serve the model for testing purposes, enable a REST API, that sort of thing. So this is something that gives us that toolkit so that we can experience, and we can continue going down that path, seeing everyone who interacted with the model, who moved it from one development stage to the other, and so on. So that's the front to back of how MLflow would be used. And if we come back to the notebook, this is why I mentioned that this is the starting point to all of that, because when we say MLflow.startRun, then that automatically opens up the opportunity to track model parameters, to log models, all these things, so that we can eventually have that level of transparency and that level of metadata collected about models. Actually, I was going to ask if there were questions, but I know that we're saving questions towards the end. I'll pause here just so that make sure that whatever time we have left, I do have a couple of minutes to take questions.
So
any questions?
it doesn't look like there's any on the chat right now or the Q&A. Can I ask one question? Is how did the feature engineering work in the CLV example?
So in this specific example,
Yes.
the features were extracted from a data set that was already pre-flattened. So we were looking at things like number of transactions, the average value of those transactions, the geographic, where are they located, and a few other like demographic basics about the user. So it was pretty basic in this example.
Okay.
And it had already been pre-flattened. Nice. And I'll share let me actually drop before I forget. I'm going to put these two things in let's see if I do this right. See Q&A, see participants. No, that's not the right way to do it. I'll do it once I stop sharing. Any questions?
Miguel, we have one that came in. Looks like from Carlos. It says it's a much nicer version of Uzi, and they said, "Is that right?"
That's a great question. I'm laughing just because I relied on Uzi heavily at Etsy. So from a automation standpoint, it is similar, and Databricks does have the ability to, once you have those notebooks locked up of what you want them to do from a data ingestion, preparation, model training, and all these things, if you wanted to automate those things, then you can create jobs that have multiple stages and have dependencies between them. So from that perspective, it is pretty similar to Uzi. Yes, it would just be a managed service, similar to it, but not directly using Uzi in this case.
Got a question from Randy Detmer. Could you compare the similarities between MLflow and GitHub?
Great question. So MLflow would be a tool to manage the life cycle of the model from experimentation to deployment. And in that context, it is similar to GitHub, that it has a specific like version tracking and all these things, but the code itself is always synchronized through GitHub. So if I come back to a notebook like this one, it still has a version history. Let's see, I know that we're out of time, but all notebooks basically have a version history associated to them, and that is synchronized to GitHub. So the code, GitHub, the model metadata, and its lifecycle would be in MLflow.
I'm going to allow one extra question here from Nathan. Are there Vim bindings in notebooks? Because I know people that like Vim really, really like Vim.
That's a good question. There aren't. There aren't Vim bindings to notebooks. Sorry.
Okay. Thanks. And with that, we gotta move on. But thank you very much, Jessica and Miguel.
Thank you.
That's good stuff. And
Thank you.
next up is Tim on R and performance analytics. So whenever you're ready, Tim, take it away.
All right. Thank you very much. Are you seeing my screen now?
Yes.
Fantastic. Yeah, so we're going to talk about our performance as it kind of scales up and down from small data to larger data. So as Doug mentioned, I'm at Centric Consulting. I'm specifically the local service offering lead for data analytics. I'm also organizer of the Cleveland R user group in the area. We've got some machine learning and R videos up on Packet Publishing. Centric Consulting is business and technical consulting, and as we mentioned in the shout out, we do have an opening at the moment with a senior data architect, so for our Cleveland practice, so particularly good for this group. I'm going to move fast because it's a longer talk shoved into a shorter time, but all of these links are up on the slides, which are at the very last slide. There's a link for the slides, so you'll see that there. So as I mentioned, this is kind of an adapted longer talk that's a survey of R and how you think about performance. And so this is everything from just making the language go a little faster, but also down to dealing with larger data sets. And so specifically, R is a bit of a quirky language. This kind of came up actually in conversation earlier with some of the other speakers. It is a practitioner's language. So in R, there's a package for everything. Everything from biostatistics, all kinds of we had talks at our user group from folks who do competing species out in environments, trying to simulate and model that. You think of it as a mathematical problem, and there's a package for it in R. However, because of that, a lot of the folks who are developing those things or writing examples on blog posts aren't software developers by trade. They are scientists, mathematicians, or in some other area. And so sometimes the code isn't the greatest or those type of things. And so R picks up that reputation. So this talk is meant to be a quick survey of a lot of things to go through it. There's demos and things, and what I decided to do was kind of leave as much in as possible, but we're not going to dig down line by line and learn how things are going. We're going to pretty much just survey to understand what's there and what's possible by topic, and then the slides kind of serve as an archive if you want to look back at things and understand something deeper, or you're free to contact me. So real basic stuff. You've got, this is an old language that started in the 70s right under the name of S. And so all of the typical Unix things you want to do out of the box are there in terms of timing, right? And it's fully giving you the same Unix convention, user, system, and elapsed, right? And for some of those graybeards, that's going to be a pretty common thing. For anybody who doesn't, isn't kind of clear on that, your user time is your code, system time is what you've asked the operating system to do, and elapsed is what happened on the wall, the clock on the wall. Benchmarking is supported strongly. There's a package, R benchmark, that's particularly popular. You'll see here we've created a vector. This is shorthand syntax. Vectors are like, you would think of like an array in other languages, and we'll square each element of it, repeat it 500 times, and I can get a full readout on what that is. You'll see us use this syntax later in the talk in terms of comparing items versus each other. So some of this is just foundational, right, to understand. So let's quickly look at that. So here we've got, we're optimizing a guess at a circle radius, right? This is a pretty simple problem, but what we're going to compare is actually the optimization packages, right? So if you wanted to use optimize or you want to use optimx and you're not sure which is faster, you can use that benchmark call. And I'm doing this, replicating, running the problem 200 times. And you'll see we'll get a list of, takes a moment to run, of course, as we purposely tax the CPU here, but you get the comparison lines, right? Particularly useful is they normalize it. So this relative column here, your shorter run is going to be given 1. And we see that in this case, optimx took almost 4,000 times as long as optimize. That looks terrible for optimx. That's not necessarily speaking to the performance of that package. It could just be a bad fit for the problem. There are other packages, TikTok and Microbench. Be careful when you Google for TikTok. You might find things more suitable for your kids than for yourself. So memory profiling is another, strong way to look at your code and objects. And so you can look at a scalar value here with this library prior that comes in. We can look at our vector object sizes, and we can look at a list, right? So ls actually gives us all variables declared, and this nasty piece of code runs it through, and it takes each one and runs it through to check the size. Again, this might seem a little obtuse. This is all kind of setting foundation for, okay, we're going to load up and create large data frames in R. That's like the base thing that you normally do. And if you want to understand how long it takes to load it, how big into the object is in memory, these are the kind of things that do that. In particular, on the memory management demo, I do want to show this code briefly. We'll just let it run to show a couple of quick things here, right? So we're simulating creating a very large data frame. You can turn on and off garbage collection information. So I'll actually tell you when a garbage collects, how it does that. It's a very useful feature. And I really like this profiling feature where you can get the memory change of an operation. So whatever block of code you pass into this, it'll simply tell you what its impact on memory is. That's a rather unique thing you don't see in a lot of other language profiling. So you can't talk about R and performance without talking about looping and vectorization. In general, you should not be writing for loops ever in the language. You should be doing vectorized operations. And you might say, what's a vector? As a reminder, that's just an array or a list in R. But in fact, everything is a vector. And this obscure code is to show that I've declared a scalar, just a value of 9 in an index, and I can actually index into it as if it's a vector, and that's valid syntax. That is because under the covers, every object in R is a vector, which is an unusual feature of the language. And you should take advantage of this. You should vectorize all operations. There's a couple of handy links in here for really long form explanations for why you should do this. Your function should take vectors and all of those things. What do we really mean by that? It can still sound a little confusing. I've got a simple vector right here of grades, right? If I take a looped approach, I'm going through each element of the array and printing it out divided by 100. A vectorized approach, division, for example, in R is vectorized. And so you see your grades, when you divide by a vector by a scalar, it just does the right thing. It understands to take each value of the list and to divide it there. I'll show the demo here. Again, we won't dig too far into the actual code of it, but the point is we're actually, so we're doing a couple of different things where we loop through and then the same operation vectorized. So I'm creating, I have a large vector and I'm going to do the square root of each number. And I can do that in a loop, or I can just pass the vector to the square root function and it will do the right thing. By comparison, you'll see that the loop is 283 times slower. Sum along is a common thing like in VI, right? Like a running total you would do. So say revenue or something like that. Sum along is a vectorized operation, or excuse me, cumulative sum is the vectorized operation. Sum along is my handwritten loop version. That loop is almost 5,000 times slower by not doing the vectorized version. So you begin to see the importance there of why you want to vectorize. So, all of this, you start to think about optimization and these problems, and people start to think about bare metal, using C functions, all those kinds of things. That is supported in R. So R itself is written in C. You can write extensions to the languages or packages in C. There's also this unusual thing called RCPP, and that is C++ right within R. There's the ugly version of this, which is where you put it in a string. right in the code. That will run and run just fine. The better version, you can actually do it as a C++ file and bring in the RCPP header. And then if you want to test that, you can even put in a comment your R code just to run a simple test. So you see this simple example here. We have a function that multiplies by 2, so nothing fancy, and then but the R code is run. And so when I run that code, it compiles the C++ and then calls it from R.
Tim, I just got to tell you, you're killing me with that prior slide of isn't there a more difficult way?
So right into our disclaimer on this, RCPP is particularly dangerous. So it manages memory a little differently than how R does. And so you can get into some real troubles doing that. People do this because they want to write in a lower level language, but prefer C++ to C. Oftentimes you're best to go ahead and get down into C and write it there. So now kind of moving into our data starting to grow, how do we deal with that in R? So one of the things right out of the bat that R does nicely that you'll notice on the Python side, like Pandas has picked this up and other places. Compressed file is our first class citizen. You just, there's support right in the language. And so I get my file handle as a zipped file and read it in. Particularly when you start to think about, for this user group, you think about big data problems. Say you've got, large transactional logs zipped out somewhere. It's awfully nice that you're not having to create disk space to unzip those things. You can just read them right from the compressed file. As your data begins to grow, you're starting to think about a data frame the size of, say, 100 gigabytes in RAM, and you want to do serious joins and those kind of things, the data table package begins to come into place. At this point, you're stretching standard data frames within R. And so let's look how that works. Not a whole lot of point to, I'll clear out the terminal and run this one in the background so you can see it happening. But this is a relatively smaller file, so it's still running quickly, but this would support very large files that we're talking about. This is flight data. And there's some slight syntax differences if you're used to data frames in R. This is a nice demo if you ever want to use data table in that, like I've put in comments, here's an equivalent kind of the SQL, right, of this, if this was a table, how you're thinking about it. It's a little odd that there's those syntactic differences from data frame, right? As much as you want to, R tries to keep things consistent across various implementations. Data table is a little different than data frame, but you can quickly come up to speed on it and then deal with large single computer data is what I would call it. Our simple ones here, right? We're filtering down by columns, selecting a carrier. Here you're doing a group and a sum. All the SQL type things are supported. One feature of this in particular I like is that, again, going back to its history and its roots, it supports shell commands. So if I know I'm only going to use certain columns, Unix types will know that this is going to cut and pick the first, second, third, and ninth field with a comma delimiter from this file. You could even easily put a head of 100 and pipe it in there or something like that when you're in development, just to cut down your data size a little bit. So again, pretty handy feature. I'm going to mention FF and FF base. I think they're becoming obsolete because of some of the other tools coming into the space. So when your data frame will not fit in memory on a single computer, you can have a data frame that is file based. And I will just pull up the code to show what the syntax looks like. We will go through the process of running it here. You can load up, you'll see I've commented out how you do this the first time. This is phone accelerometer data, and you'll save it out into a serialized special specialized format. Any operation on that database will batch it out to disk and operate over the file size. There's specialized libraries like this big GLM that'll do a linear model using those objects. But the fact that you have to do this kind of thing means that the standard machine learning libraries and models aren't easily there or available. That combined with the growth of various clustered systems, I think is making that relatively irrelevant. Parallelization and multi-core support is strong in R. Just because I want to leave time for questions, I think we're going to skip that demo. Just know that it's there. Deep learning support. So for large data sets, as you're doing deep neural networks, GPUs are a great speed up. So there's links in here to talks that Brian Lewis did one and I did one at the R user group about using those the R implementations of TensorFlow and Keras. They actually use Python virtual environments under the hood, so it's kind of clever. It's R language that calls through the reticulate package and marshals the data into Python and works there. There isn't much of a speed performance as you would think, but you do have to ask the question, right, why not just do it in Python? Most folks doing pretty serious machine learning are going to know multiple languages or be Python's pretty comfortable there. I would say, and those libraries are first-class citizens within Python. So, the use case here, I think, is if you have a team that's strongly in R and you're just beginning to get into deep learning and you want to do a comparison, it's a great proof of concept tool. I would not, if you're going to do serious long-term machine learning, you would be best off doing it in Python. As data moves up the chain, and this is why I said I think FF is falling out of popularity. You're really going to look at tools like Spark, Hadoop, H2O. Obviously, Databricks just presented as another great option. But I think all these tools have good support for R, and you're going to take advantage of the higher platform of MapReduce and whatnot. I did put this in here. I really love. So Hadoop becomes a prominent member of the R community. Works in R Studios, written many R packages and most important R books. And I love his big data definition. It's that big data comes into play when CPU time for calculation takes longer than the cognitive process of designing a model. I love that definition actually will scale over time as opposed to someone just saying terabytes. If you're dealing with some of these issues and you're looking for help in R, these are some of the more common popular places, as well as the link locally for our user group if you want to chat with anybody there about it, as well as a blog post on the best way to write reproducible examples in R. R's got some actually specific functions and packages just for that problem. I blasted through this all pretty quick, so if anyone's trying to copy links, here's the place to start. I've got the slides up there. It's actually in R, so it's a R Markdown presentation, but they're exported to HTML as well. So you can just click through the HTML slides and get any of the links you want. And by my kitchen timer, we've got about a minute for questions.
Yep, I think, so Carlos had one earlier. Does the compiling of C++ code execute in line? Is it a separate process? And how does it affect performance? I think this was back when you were talking about is there an even more difficult way to do it?
Yeah, it is in line because of the necessity of it being available when the code runs, right? If it was out to another process, you'd have to block anyways to wait for that to be done. There should be ways, as I recall, to save the function declared out to our data files, and then you would reload those things up. That could be a little like locally cache or compile. Again, if you're regularly heavily reusing C, I would look at writing a C extension. And honestly, I think I showed this in somewhere. There's an RCPP benchmark. Let me run that in the background while I'm chatting here. So we actually In this, I put in an example where you do RCPP to do the mathematical operation. So this was a distance optimization issue, and R vectorized is still faster than the C++ implementation. In general, be careful when reaching for RCPP. So
good stuff. Hey, thank you very much, Tim. Everybody give
Thank
Tim
you.
a hand, and yeah, great stuff.
Stop presenting here.
And Fanny, you're up next, and whenever you're ready, take it away. Yeah, it looks good. I can see it.
Yeah. So you can also hear me, right? I think I just now
So that's correct. I can hear you.
Okay, great. So thank you for inviting me for the presentation and sharing our work today. So I'm going to introduce our developed AI-driven system named Alpha Satellite for dynamic COVID-19 risk assessment in the US. I'm now currently an associate professor in the Department of Computer and Data Sciences at Case Western Reserve University. Before joining Case, joining academia, I've been working in industry for over 6 years. So my main focus in research include AI and also its application in cybersecurity and health intelligence. By collaboration with my industry partners, we have proposed and developed a cloud-based solution for mining big data in the area of cybersecurity, especially for malware detection and adversarial machine learning. And recently, I collaborate with other colleagues in both WVU and CWRU. So we have expanded our research on health intelligence with focus on combating opioid crisis and also COVID-19 relief. So this year, we have been going through the tough moments like the COVID-19 pandemic, the global pandemic, and this deadly outbreak exposed global and also national challenges. It also created a series of variety of other crises such as unemployment or mental health problem, or it also make drug abuse, opioid abuse increase sharply. So combating COVID-19 pandemic is one of the most urgent mission for us this year. And since the very first case of the coronavirus outbreak in King County, we have been aware of this kind of community transmission. Before a vaccine became available and also widely deployed, a community mitigation could be the most readily and also applicable way to have slow down the spread of the virus. So we also aware a growing number of areas reporting local community transmission would represent a significant trend for the world in the battle against the coronavirus.
770.
So this points to an urgent need for expanding surveillance so that we can better understand the spread of the COVID-19 and better respond with actionable strategy for community mitigation. However, we still need to we still have the essential needs such as grocery shopping, or go to see the doctor if needed, or go to the pharmacy stores. So in this way, in late February, when I was in DC for an SF workshop meeting, and I just think, okay, so in this case, there are multiple choice we can have. If you need to go to the pharmacy and there are so many nearby pharmacy stores, then which one I should go with a lower risk, and which one I should try to avoid? Probably that would have a higher risk compared with others. Is there any possibility we can provide data science driven, AI driven tools for the community we live in to provide a dynamic COVID-19 risk assessment at community level? to have like to have for the actionable information to combat this kind of global pandemic. So motivated by this, then since early March, since I came back from DC, and then I have led the team to develop an AI-driven system as an initial offering to provide dynamic COVID-19 risk assessment in the United States. And more specifically, given a location, either user input or automatic positioning, the system will automatically provide risk index associated with this POI in a hierarchical manner, like for this specific location for the POI, point of interest user provided, what will be like a relative risk, and we are also going to provide the associated county and state level to help people to select appropriate action for protection while minimizing disruption to daily life to the extent possible. So the data we use, including 4 aspects. The first part is like a disease-related data, including like for example, like the confirmed cases number, the new cases in this area, and also the fatality rates, the death number, and so on. And we also consider like demographic data, for example, like the population density in this given area, and then the medium income, the education level, and so many others, like so, and also like the distribution of the age, because like other people compared with the younger generation, that could be more risky to get infected by COVID-19. So we also leverage this kind of information for the estimation of the risk. And we also consider about the data from social media. And the first offering, we leverage the data from Reddit and Twitter. So we would like to have like the perception in terms of like how people perceive about the COVID-19, whether they take this seriously or they think like this is not a big deal. And we would like to use this information to have the estimation of the COVID-19 risk. For example, if people take this seriously and were prepared for like physical distancing and so many others, then compare with like another area, if people like didn't very aware of the COVID-19 risk and didn't take like appropriate actions, then this area compared with like the former discussed area, it will be more risky. And we also consider about the information from the mobility data. For example, like how dense the traffic it is for this given area. And we just like leverage all this data from heterogeneous data source to build a model for the estimation of the COVID-19 risk. So basically based on the data we collect, then we build a network, which is like a heterogeneous information network. And for this constructed network, we use like the information we collect from the first aspect for the data source to estimate for any given area what is the related risk it will be. And then for one thing I would like to particularly mention is like for the social media data, because they not all like a given area, there's the discussion in social media in terms of how risky or like the public perception in terms of COVID-19. So we leverage the AI-driven technique condition again to like estimate like what is the people's or what is the public perception for like those area where the data are missing. And in this way, we build this like we enrich the constructed AHIM by using the condition again. And in this way, we use like a graph neural network to build the end-to-end model for the estimation of the related risk for any given area. And you can directly, this is like a web application. You can directly access our web application. The service provided by Alpha Satellite through like a web address covid-19.yes-lab.org. So you can directly visit our website, and then you will see like the related risk of any given area if you are interested in. And then we also provide like a dynamic map as well as like a other analysis board. So I probably would like to give a very quick, I would like to give a very quick demo for like a website.
Go for it.
Yes, okay, so this is our website. You can directly visit our website through this address. And then when you like access this web application, then you will directly provide the correlated risk index for this given area. This is like where I am. And then this will give like the risk index. The higher, the more risky. And also the traffic status. Traffic status means like how dense of the traffic of this area. It will range from 1 star to 5 star. The lower means like the less traffic. The higher star, like if 5 star means it's extremely traffic. And this data is provided by Google Map platform. And not only like providing the risk index for like this particular POI Euro query, but we also provided like the related risk in a hierarchical manner. That means your associated county and also your associated state. So for your associated county, you can see like the risk percentile among all the counties in Ohio, and also like for like the risk percentile for among all the states in the country. So we can see the dynamic here, and this is like automatically provisioning for my current area. And then you can also like see, for example, if like our initial like intention is like, okay, if I would like to go for grocery shopping, grocery store near me, and then when you query this, then you will provide it like a grocery nearby, and this will provide you like a ranking list, like per risk index from low to high. Then it will facilitate the users to pick which store you might want to consider if you need to go for grocery shopping. And this is like, for example, one of the grocery store nearby my current area. And then you can see like how traffic it is, and also like the demographic density for this given county, like how many people per square meters in this given county, and also the related risk index. And you can also provide your feedback in terms of how risky this place it is, like from extremely low to extremely high. And you can see actually in this panel, you can also see like the new cases, and also like the correlated like numbers for like the county and also state. And in this way, you can, this is not only regional map, but also national map. For example, we can also query like, let's say New York, grocery store, Manhattan. And you can see here, I can also query like other POI in different city or like a county, state. And then you can see like this will display the related like a risk index. Then like right now, like New York State would be like a 69 percentile among all the states in the country. We know like things like late June, there's the second there's a surge of like the increasing new case number, and Florida is like the highest new cases things late June. And then you can also see New York City among all the counties in in New York State. It's the highest like risk compared with other county in New York State. So this would be like the dynamic map, and this is not only regional map but also national map. You can query whatever you are interested in, and this also provide an analysis board to facilitate like a more decision making for any organization or even like an individual person. This provide like a risk percentile per state. And then this also, we also consider like the traffic transmission. That means like, for example, this is like the top 10 traffic flow in to Ohio in the past 2 weeks. And then we can see like the most traffic would be from Kentucky. And we also leverage this like a nearby nearby information, nearby locations information for the estimation of the given area. So that means like if there's like a significant traffic flow from other states, then we also need to integrate, aggregate the nearby areas information for the estimation of the given risk, of the risk, sorry, given areas risk. And we also provide like a recent risk percentile per state level or county level. So you can select like whatever state you are interested in, and then in this state, whatever county you are interested in. And this also like the case and death growth rates, and also the case number, as well as like the new case trend analysis and percentage of the new case over versus overall test. You can see like this would be the percentage of the the new cases versus like always a positive rate actually. And then you can also see like this is the new case trend analysis at county level. And we also provide like on daily basis, like the risk assessment, the percentile per all the states across the country to facilitate like any decision making for any organization or like policy leaders. And here we also provide like a user survey, and also like in terms of like how you feel during COVID-19, and the dynamic map, as well as the analysis board. So basically, just now I demo like the web application, which already launched for public test and uses. So if you need such kind of service, you can directly access our website. And we also have like the general publication published in Journal of Biomedical and Health Informatics. And this paper provides the technical details of the system. If you are interested in, you can directly access the paper. And we also like would like to share like the broader impact given by this system. After we launched the system for like alpha and beta test, we launched the system for alpha test in early April, and then beta test in late April. And since the beta test, since late April, by today, we have like about 100,000 users for this web application. And you also received the Metro Lab Innovation of the Month Award in this May. And we also like we have also receiving a lot of good feedbacks from the users in terms of its ease to use, as well as the utility for the relative risk estimation. So my motto is innovation, research, and education for a better world. So I truly enjoy finding normal yet elegant solutions to resolve the real world problem that generate high impact. And the long-term goal of our research is to advance capability and trustworthiness of AI to provide state-of-the-art innovation for cybersecurity, and also improve the health and well-being of people around the world. And welcome for any possible collaborations. And this is our project team. I work with another professor, Ken, and also he introduced me to this panel and the presentation today. And this is like my lab member. So if you have any questions, you can send me email. And thank you very much. And that would be basically for today's presentation.
That is a fantastic looking website. There's a lot in there. What's the technical I know there's 2 minutes left, but what's the technical stack? Like, what did you build that in?
You mean the technical challenges or technical?
Oh, just can you talk a little bit about like what
kind of technicals we use? Is
yes.
that right? Okay, so first of all, we need to collect like the data from heterogeneous. So like collecting those up-to-date data, actually you need to overcome a lot of challenges to make it less datable. And then secondly, based on this collected data, how can you build a powerful model to depict or to describe those kind of multi-source data with different kind of format? It's like a heterogeneous, including like a structured and unstructured data. How will you deal with that? And then how will you connect all these kind of multi multiple type of entities and also relation. The third technical part is like, okay, based on your build network, then how will you devise AI-driven model to give the estimation of any given area in terms of the COVID-19 risk? And then let me give a very specific example. So if you would like to leverage social media data to give like the estimation of the public perception in terms of COVID-19, and you are going to encounter a lot of cases like the data are missing for this given area. And then to estimate like this area's public perception in terms of COVID-19, we use the conditional generative adversarial network to devise like the synthetic factors to give the estimation. And this is one of the aspects. And then after you enrich the data for the build a heterogeneous information network, then how will you estimate the risk? Then we are going to use the one of the emerging techniques in AI called the graph neural network. Then you are going to devise the end-to-end model to give like a real-time prediction.
Could you put your contact slide back up, please? We've had a request for that.
Sure. This is my contact information. This is my email address. And then you can also like, if you are interested in, you can also visit my website. I periodically update my website, and then that would include like our most recent research. So you will be like yes-lab.org. So you can just like visit yes-lab.org, and then you can through this website to easily access our COVID-19 web application.
And if you could do one last question from Randy, did you use Mapbox with JavaScript and D3 to create the website?
Sorry, can you say it again?
Did you use Mapbox with JavaScript and D3 to create the website?
Okay, so for like the website development, yeah, we mainly use like Java, but like for like the framework, I think they use like my lab, my students like mainly use a synthetic web framework. But I may need to recap like what kind of framework they use. But you can send me email in terms of the detailed question. I can get back to you.
Okay. So I think that's it. Again, let's give a quick virtual clap and a round of applause for all the speakers. That was fantastic, Fanny. Thank you very much. And again, thank you for the rest of the speakers. Thank you for the audience for showing up. And yeah, I can't thank you enough. And we're going to be meeting again in November. So yeah, the hands clapping, great comments coming in. Thanks, everybody. Everybody have a great night. Thank you. Mask up.